Welcome to a new test and teardown video. This time it's a Fluke 1900A multi-counter. I bet that will be LED. It should be 6 digits and it should handle all the way to 80 megahertz as it says here. And with 6 digits I expect this one to have 1 hertz resolution at 1 megahertz, of course. So this is something we should test. Yeah, I keep getting all these cool Fluke instruments. Fluke is a brand that I really like and enjoy. The initial design is from 1975 and they end this model in 1984. So maybe we can find some clues inside. How old is this one? So this is a classic way to open these Fluke instruments. You remove this screw and then you just pull everything out in one go. But be careful, it's not super strong and steady, all this, so you have to be a little bit careful because sometimes it grips like here, and if you just pull you can break those little plastic tabs here. So that is a classic problem, but see, now it's out and then it's perfectly fine. There's no solder mask on many of the old Fluke instruments, so it's of course a little bit moisture sensitive. I would prefer to have a solder mask. And here is how they interface to the entire front display system here, and that is really nice. This is not what we call a flex PCB today, but this is just a thin 2-layer circuit board. See, there's no wires, there's no connections or connectors or anything like that. You just solder the LED displays directly into this thin circuit board, and then it's bent into place, and then clickety click, and then stick it into the main board, and then just solder all the connections. And they use this area to move a little bit of the connections around, so they didn't have to move a lot of it on this motherboard. And that is of course because it's only a 2-layer board and you need to be able to do all those connections and all that. And I believe this IC is a, well, somebody removed the numbers, but that's just a standard frequency counter chip, I would assume. And it looks like somebody's been servicing this one a little bit. We got some visible resoldering around the power supply. And this looks like there's supposed to be a heat sink, and that was not mounted. See this, the holes and all that kind of stuff. But that is the first impression is so far so good. All is nice and fine. So let's try and power this up and see what happens. So I dim the light a little bit and let's see what happens. And this is a classic thing. It's using about 2 watts at the moment. I just turn on mains input, and that means that this power switch is after the transformer. So this is on secondary side, and that means they don't transport mains voltage all the way to the switch and back, because we got counters and all this. We don't want high voltage going all the way back and forward. So the transformer is actually always on, and then you have a low voltage secondary that goes via the switch, a DC voltage. So there's nothing to interfere with the counter. And it goes on and it's indicating the kilohertz. So I am in auto mode and frequency mode, and I didn't do anything other than that, let's try and input a signal like that. So this is 1 kilohertz, and then it goes in auto mode. You can of course go into manual mode like that, and it should give you exactly the same. So this is, it says here 1 hertz, but if you move it one more to the right, you'll have 0.1 hertz. This is of course not one of the auto settings because it takes 10 seconds to do, to do a frequency count, but then you have 0.1 of a second resolution with a 1 kilohertz signal. So let's go back to the 1 hertz. That takes, yeah, of course, 1 second. So that was 1 kilohertz. So how about we do 1 megahertz instead? Then, oh, see, we got 6 digits, but we don't have 6 zeros. So to be able to write 1 and 6 zeros, that means you need 7 segments to do that, and this one got only 6. So we need to move the decimal, and now we have 10 hertz resolution with the 6 digits. So that is what the 6 digits of course means. What we can do is we can write 9.9 megahertz, and then you will have it right here, 9.9 megahertz. There's a decimal right there, but that is for kilohertz, I believe, because then you have 3 more, and then it is mega. So that is the way it works in frequency counter mode. It's a little bit dim, especially this little dot, but I think it's just cleaning. I'll try and clean it a little bit and see what happens. Oh yeah, it's also a little bit off. So there's a little crystal, and we should be able to tune that. I was right about the glass. Look at that. Here in the light, it looks so smoky. I should probably just try and see if I can get this glass out and see if I can clean it from both sides. There will be a trick to do that. We can just take these little rubber holder thingies, and then we can just not that easy, because if I'm supposed to do that, then I will break this. Oh, no. So I need to unscrew here, and then it should probably work. So that made it. I didn't desolder this connector down there, so I just pulled it a little bit in this side, and that was enough to carefully bend the board out here. Now I'll try and clean the acrylic glass here from both sides. Probably gonna help a little bit. Well, that was quite funny. When I tried to clean it, I accidentally pushed it, and see, we got those little locks here and here, and then of course I still needed to unlock these, but I could have done it a lot easier. See, we got some nasty stuff going down here, and I cleaned it a little bit more here, but it's still really not that transparent. And most of this out of focus kind of stuff is here on the front. So this tells me somebody's been cleaning. It's totally out of focus, look at that. It's probably also the camera, but there's definitely something wrong with this acrylic. And it looks, yeah, well, so somebody cleaned it with something that destroyed the surface. I don't know, did that help a little bit? Maybe the dot is a little bit more visible. And this, the LED in here is really, really bright compared to everything else. So that is a little bit stupid. It should... I think I can fix that by changing the series resistor to those LEDs there, because that is just dumb. And I'll try and see if I can adjust the little crystal here. There's a crystal oscillator with a variable capacitor right next to it. So Okay, see? And there you almost have it. I always play with numbers that goes like that because it's better for me. But I think there's a thing that is not so smart because I have the next one, 5, 6, 7. So it's gonna flip from not 5 to 6. So that is a little bit off, isn't it? But it's the last little, yeah. So we want to see 6 and then sometimes 7. There we are. How nice is that? And if I tune the last digit a little bit. Should be able to get a stable signal like that. Oh, this is funny with the font. So number 6 don't have this line at the top. So there's only one little thing to do here, and that is to test the maximum frequency. And it is rated 80 megahertz, and this is what we got right now, 80 megahertz. So let's just try and crank it up real good. Let's just try it. Okay, 90. Oh yeah. Okay. So it's probably gonna overflow. So that is 101. Okay, so I can continue. What the? And then it goes ploppity ploppity. So that was, let's go back, 100 and, no. It's still a little bit weird. Yeah, stable 106 megahertz is the maximum frequency for my unit here. So that is a pretty good margin, wouldn't you say? How about we enjoy the internals a little bit more of this counter? Of course, the input goes via a little coax cable to the first input amplifier. And all this is just amplifiers all the way. And then the last stage is I think it's like 3 or 4 saturated amplifiers inside this chip. And then it goes in here and is now a fully digital signal. There's an attenuator, so you can handle more or less input. And there's also a filter, low pass filter, 1 megahertz. So if there's some overtones or some harmonics or some problems at higher frequencies causing problems, then you can enable this 1 megahertz low pass filter. We see some special chips, just this first one here. This one is a Mustang special chip, and I just googled this thing, and as you can see here, it's worth $50 for one chip. It is a programmable divider with a clock input from the oscillator system, and then of course 4 bits that selects all the different timing setups, and then out goes the pulse that goes to the main gate. And then the main gate is counting whatever it is you have as your input, and this goes into this chip here. And this, they call this U22 on the circuit board, but in the schematic it's called a U24. So that is a little bit funny. U24 is a very complex chip, full of all the counters and latches and multiplexing, display driving and all that kind of stuff. You got 4 bits output that goes to an external 7-segment decoder, and then the 6-segment enable signals, and all this goes to those 2 chips here. There's actually an external latch again, and then the 7-segment decoder, and there you have the transistors needed to drive the 7 segments using this flat cable. And that is more or less all there is to it. All the other chips, they just handle overflow, this and that, and handle auto ranges, and not a lot of complex things going on, but they are using a lot of chips to solve all those things with. But it is in a really, really good shape for its age. And about age, if we look a little bit careful on the different chips, we can see there are 74 and 75. So the highest is 75, so I believe this unit is from 1975. And I'm quite happy about that. So I think that is more or less all I wanted to show about this nice Fluke frequency counter. So thank you very much for watching so far. See you around. Bye bye.